in physical properties, and less work has been done on the mechanical properties. Now, I'd argue that understanding how mechanical properties change is more important. We can think about this flexible electronic here, where oftentimes they'll put the polymer film into the neutral layer, where when you bend the device, no stress is felt. If they put it on any other layer, it'll often lead to the earlier failure of the device. So really, I'm interested in how mechanical properties change at this ultra thin state. But you're probably wondering, what do I mean by ultra thin? How do I define that? That's a weird metric. So we can think of a polymer in 3 different size scales: 1D or single chain here, or 2D, where the film thickness approaches the average molecule size, which we define as the radius to end-to-end distance, which I'll tell you what sets that in a few slides. And so this is what we define as ultra thin. So, and then most of the work that's been done on the mechanics has been done in that 3D or bulks-like state, where the molecule size is much smaller than the thickness of the film. Where here we have a typical stress strain curve for polystyrene, and this is a tensile one, though I'm bending this piece of plastic here, where they're able to stretch it. And this is for polystyrene, which is a model system that's very well characterized in terms of the mechanics and changes in physical properties. And it will be the polymer that I use throughout this rest of this talk, and the one that I majorly studied during my PhD work. There's also been work done on the polystyrene down at that single chain limit, where here is in a force extension curve for where they do AFM, they stretch that chain. And you can see that the force extension curve for that single polymer chain differs in shape from that bulk stress strain behavior. So it leads to that question in this ultra thin state where we have a 2D layer, where now we just have a single polymer layer of chains. What is that stress strain response? Where I'll note the polymer film I'm playing with up here is microns thick. So we're thinking about 1,000 times thinner than that, so nanometers thick. So we can't actually play with these, and this is part of the reason why they've been so difficult to handle, because they're very brittle in nature, and you often can't see them or even pick them up freestanding. So in this work that I did during my PhD, I really did uniaxial tensile testing of ultra-thin films, where the first area of the talk I'm going to be talking about is the failure mechanisms that are occurring in these ultra-thin films and how do we quantify them, and then understanding what controls the mechanical properties in these states, where we'll look at understanding how the physical parameters that change in these ultra-thin states relate to the mechanical properties that we measure. So before we go into that, I'm going to give you a little bit of background of what sets the physical properties, so that polymer size and these entanglements and what gives its network integrity. And then 2, what do we know about how physical properties change in these ultra-thin states? And then what other measurement methods that have been previously developed in these mechanical properties measurement techniques before my work. So for the polymer's characteristics, we can think of that molecule size or that radius to end-to-end distance I talked about a few slides ago. And this is dependent on the chain length, or the MN, or the number average molecular weight. So as you have small chain lengths, you have a small polymer molecule, and as you increase your chain length, you have a larger polymer molecule. So how we define ultra thin, you have to think about those molecule sizes. So, and only when they become approach that molecule size do we become that into that confined limit. The other thing that we have to think about in terms of polymers, especially these glassy systems, is what gives it that network integrity, considering there's no covalent bonds between the polymer chains, as they're just these single chains that we can think about as a bowl of spaghetti. And one of the things that gives it the network integrity are entanglements. So these are the physical interactions between the chains. So if you cook up a pot of spaghetti, and you mix it around, you pick it up, you'll get many strands that are interconnected. So what controls this on the molecular scale for these polymer chains is the entanglement molecular weight, or the length of the chain that it takes to form an entanglement. So as you increase your molecular weight, there's more entanglements per chain, or more MN over ME. And so we really need to think about how entanglements change in these ultra-thin states. So if we think about there's some nice work developed by Dijens and Silverberg that's been used to develop scalings that as you approach that molecule size, that radius to end-to-end distance, that you have a change in entanglement state. They proposed that as you got into this thin state, the molecules became more entangled with themselves and then with their neighbors. So you have a loss of interchain entanglement, which would lead to what happens in terms of the mechanics. And this has been experimentally inferred, but hasn't been directly measured and has been shown through simulations. There's another property that we need to consider that's been shown to change and is probably more well characterized than these entanglement changes, is the average molecular mobility. So in a glassy state where these polymers are, so the glass transition temperature, or the temperature where it comes from brittle to ductile, is around 100 degrees. We're looking at these systems around 20 degrees. And there's an interesting property that occurs where at the inner bulk layer, they have the same glass transition temperature, but there's a surface layer where they're more mobile. So when you decrease that thickness, that mobility now increases in that system. So you have an increase in average molecular mobility because these mobile surface layers are taking up a larger volume fraction. And this has often been shown as a depression in the glass transition temperature and has been very well characterized in the thin film community. But so we know that these two properties can change in these ultra thin states for physical properties. There have been measurements done for mechanical properties. And the three common methods are surface wrinkling, nano indentation, and nanobubble inflation. And these are all limited in the low strain, where we can look at the elastic modulus, where for polystyrene, the elastic modulus as you decrease thickness has been shown to decrease with the surface wrinkling technique. Whereas with nano indentation, it's been shown to increase with decreasing thickness, and similarly with nanobubble inflation. So even with this model polymer system, there's disagreement what's happening in these mechanical properties in these ultra thin states. But we're really interested if you think about the applications of those flexible electronics of how polymers fail. So there have been other methods developed to look at these failure properties, including the copper grid method by Kramer and coworkers, and the crack spacing method down at NIST, where they've shown that no change in craze strain happens as you decrease thickness from Kramer's work, whereas they've seen an increase in the fracture strain and a decrease in fracture stress in these crack spacing methods. But these high strain methods have been indirect. And so they haven't been able to quantitatively measure. So either we can measure these low and high strain responses, but there's no unifying measurement technique that accesses both the low and the high strain regime. And we're really interested, can we create a measurement method that can capture both of these? And really there's been limited direct measurements, where the only method of the 5 that I just talked about that is a direct technique was that nanobubble inflation technique, and that's under biaxial loading. And as I mentioned, it's really difficult to quantitatively measure these failure and deformation responses. So this is really one of the goals I set out to do in my PhD, is understand what is the failure response in this ultra thin state, where we're going to look at the thickness effect specifically. So before we go into that, we're going to go a little bit of a review over what are the bulk failure responses of these systems. So there's 2 for glossy polymers. One is a craze and the other one is a shear deformation zones. One, crazes form perpendicular to the direction of stretching, and if you zoom in on them under electron microscopy, you'll see a void in fibril morphology. And these fibrils are load bearing, but they're often associated with brittle behavior, whereas with shear deformation zones, they form 45 degrees to the direction of stretching, where they're drawn polymer regions, and they're often more desired for tough materials as they're more ductile-like. So polymers like polycarbonate undergo shear deformation zones, whereas polystyrene undergoes crazing. So what sets if a polymer that's below its glass transition temperature undergoes crazing versus shear deformation zone? And so Kramer again has done some really nice work on this, where they created this phase diagram of temperature versus the entanglements in the system, or what we'll call the 1 over the ME, or the entanglement density, where you can see that if we keep the mobility constant, we keep the entanglements constant in the system and increase the mobility, or that temperature, we'll transition from crazing to shear deformation zones. But if you have a low entangled polymer and keep your temperature constant, you'll go and increase the entanglements in your system, you'll go again from crazing to shear deformation zones. So if you have low entangled polymers like polystyrene and polymethyl methacrylate, they undergo crazing, where they land on this part of the curve. Whereas if you have high entangled polymers like polycarbonate, they'll land on the shear deformation zone part of the curve. So we know in the bulk that that crazing is typically associated with brittle behavior, and polystyrene typically undergoes that, but shear deformation zones are associated with ductile behavior, and either increasing mobility or entanglements leads to this transition from crazing to shear deformation zones. But in the thin film state, we know as thickness decreases, that the entanglements decrease, which would suggest that we'd only see crazing. But we also see an increase in average mobility, which potentially has a path to go from craziness to deformations. So this leads to the question, when we decrease thickness, will we see crazes or shear deformation zones? So to answer this question, I developed this instrument called the uniaxial tensile tester for ultra-thin films, or TUT-TUT for short, because that's a very long name and we really like fun acronyms in our lab. And this was inspired and really developed off of previous graduate students' work in the Crosby group, where I've extended it to look at the failure responses, where it essentially is a cantilever-based method with a reflective coating with an extension piece in it that allows us to do in situ microscopy so we can see if the film forms crazes or shear deformation zones as we're stretching it. And then we have the film connected to that extension piece and floated on the liquid bath support layer, and then clamped in to a 3D printed bath. This bath sits on a linear actuator here, and this linear actuator can translate in this direction, and our cantilever is fixed. So as we translate our linear actuator at a fixed speed, we'll stretch our film and the cantilever deflects. And we measure those deflections using a laser source and a white screen. And those deflections are calibrated for force and displacement, and from the film geometry, we can calculate the stress and strain. While this is a liquid supporting measurement, I also developed a freestanding measurement because I was always getting questions, what about the liquid? And so we developed the uniaxial, the tensile tester for ultra thin freestanding films, or TUF for short, because again, we like fun acronyms and it's tough to do. And it's basically the same thing as the TUT-TUT measurement, but now we have a support frame. But for the work that I'm talking about now, and really provides capabilities for going beyond polymers that are not water sensitive. But polystyrene isn't water sensitive. So for now, we're going to only use TUT-TUT for the rest of this talk. So to probe these failure responses, we're going to take mica as our substrate. We're going to fleshly cleave it to create a clean substrate. We're going to spin coat polymer films of polystyrene from 20 nanometers in thickness up to 360 nanometers, where the molecule size of this polymer is 25 nanometers. We'll then anneal them to remove the residual stress and residual solvent, and then we'll laser cut them into this dog bone shaped film, which allows us to concentrate the stress in the gauge regime. And then we'll float them off into TUT-TUT. So here we have a video where you can see that I'm floating off this piece of mica, and you can see the film goes on top of the water and the mica separates down, and I'll release the mica and we'll have the film floating on top. So we have the cantilever over here, and then I'll drop the silicon wafer down and keep lowering the water level down till the point where the silicon wafer sits within this clamp system. You can also see as I'm lowering this down and positioning it that we have the microscope above. So as I continue to lower it down, there's actually 2 magnets underneath this clamp, and I'll bring 2 screws in, which allows me to clamp in that film to be fixed, and then I'll raise the stage up to bring the film into contact with that cantilever. So here is a typical test. So we're looking from above right here, and this is one edge of the film here, another edge of the film here, and we're stretching in this direction. We have a stress strain curve down here that is for this film, where we'll have a red dot that will track throughout. We have a linear regime, a yield, and a plateau. If we go towards our yield point, which is right here, we'll see that lines form perpendicular to the direction of stretching. And this was expected as this is a 300 nanometer thick polystyrene film. So if we go a little bit further towards the failure point, we see lines form parallel to the direction of stretching. And these are tension-induced wrinkles, which we don't think is playing a role in our measured stress strain response. So we can now watch these crazes form, and then we won't see the failure point due to the fact that the camera doesn't always capture that because we're only looking at a small area. So as I noted, this is a 300 nanometer thick polymer film. What happens if we go down 100 nanometers? So here's a 200 nanometer stress strain response, where again, you see a linear regime, a yield, but now a softening in your stress strain and a plateau. So this molecule size is 25 nanometers. So we're still in what we would consider bulk, where you can see it from this nice cartoon. What would happen if we decrease our film thickness now and approach that molecule size down to 30 nanometers, where we're still above that molecule size? We can see, again, we have a similar stress strain behavior. We have a decrease in that maximum stress or that yield stress, but we still see a similar shape. So what happens if we decrease our film thickness by 10 nanometers? now approaching and decreasing below that average size, where now we're only 5 nanometers below that, where we're what we consider confined. We see a drop again in that stress strain, but we see an embrittlement where we don't see ductile-like behavior, and potentially a change in that linear regime where we measure the elastic modulus. And if we go into our dark field microscopy, you can see that we have these shear deformation zones forming. And this was really surprising for us when we first saw it, because it wasn't our initial hypothesis of what we would see, but this is the first observation of a thickness control transition from creasing to shear deformations. And so we can watch these form in this video where we're still stretching in the same direction, and the failure point is actually captured in this video, and it'll be right on this right-hand side. So you're probably wondering, did we check under electron microscopy? And we did, and we saw for the 200 nanometers and the 30 nanometers that void and fibril morphology typical of crazing. But for the 20 nanometers, we saw no void and fibril morphology and just drawn polymer regions. So again, we confirm, right, we have these shear deformation zones forming in the system. So if we go a little bit, but we didn't only just, so what is leading to this transition from crazing to shear deformation zones? So if we go back to that phase diagram I initially showed you at the beginning of this area, where one, we know that either increasing the entanglements changes this transition, and we know that temperature increases this transition, but we also now know that thickness leads to this transition from crazing to shear deformation zones. So if we go back to what we know about what happens in thin film state, one, we know that the entanglements decrease with decreasing thickness, which suggests we would only see crazing, but we're seeing that this increased average mobility as we decrease our thickness is potentially leading to this transition from crazing to shear deformation zone. So our observation suggests that the increase in average molecular mobility is having a larger role on these properties than the change in the entanglements in these systems. So we can now create a phase diagram with mobility or temperature as a function of thickness, where you can see that we can go from crazing to shear deformation zones for this literature values up here for in the bulk. Excuse me for a second, it's very warm in this office. If we go down another to 700 nanometers from the Kramer and Berger data, again, you can see that they don't get into that transition regime for these bulk entanglements, but again, we're below this, what we call the transition temperature line. If we now put our data on here as a function of thickness, you can see that we have a decrease of this transition line, and now we get that thickness-induced transition. And this is really more of a proposed phase diagram, providing an opportunity in the future to explore how temperature impacts these in failure mechanisms. And really, again, that we saw this potential decrease in this transition temperature, and really this change would be an effect of that increase in molecular mobility. We didn't only look at the failure mechanisms, we did measure that stress strain curve. And so if we look here now from our stress strain response, you can see that we can get from the linear regime an elastic modulus. So we have the elastic modulus plotted against a function of thickness, where you can see as we decrease our thickness, it looks almost constant, though I would argue a little bit that there might be a drop here. And if we compare to our previous data on the rectangular films and the surface wrinkling, the two lower data points are in agreement. Though in terms of elastic modulus, they're usually pretty varied in terms of the literature of what values you get, and they're very instrument dependent. So really this drop in elastic modulus has previously been proposed to be due to that increase in molecular mobility, which again suggests that observation of that shear deformation zone that we saw is due to those mobility effects. So we can also look at the failure strain. So here we have failure strain plotted as a function of thickness, but you're probably looking at, wow, those are really, really large error bars. How can you get any information out of them? And so really this is due to the fact that failure strain is very defect dependent. And so we're not going to pull any information out of these, but I will show you a data set from our largest error bar where you can see here, this is stress and strain for this 100 nanometer thick polymer films, where you see that one, we have that large scatter in those failure strains where we were even getting out to 10% strains, but we have less scatter in our maximum stresses and our failure stresses. So we're going to use our maximum stress as our indicator of what's happening in terms of failure. So here we now have maximum stress plotted as a function of thickness. And you can see that we have a slight decrease in our maximum stress if we decrease our thickness, but we have this large drop when we form those shear deformation zones. And this was really surprising to us initially, because we could think about typically, and we have a drop in the failure strains if you look at this representative curve. This is surprising to us because typically you think of a shear deformation zone as very ductile-like in behavior. So one of our initial hypotheses is that it's the embrittlement is due to this interchain entanglement loss, that when you decrease your entanglements, you're having a higher force per entanglement from this picture right here, which is leading to earlier chain scission of the film. So we did a little math to figure out how many entanglements we're losing in our system. So the initial film had 7 entanglements per chain, but if we decrease into that 20 nanometer thick film, there's now only 6 entanglements per chain. So we do a further math of what percentage of this maximum stress drop is and comparing to the entanglement loss. We can see for the load-bearing entanglements in the system that there's 85% of the bulk, but the stress drop is much larger. So leads to open questions whether or not this embrittlement is just due to this entanglement or there's something else in play. And that's kind of what I'm going to be probing in the second half. So in this first half, I looked at what are the failure responses of the ultra-thin films, where we did a direct measurement of uniaxial stress strain response of these films down to 20 nanometers in thickness. And we saw for the first time this transition from creating the shear deformation zones that was thickness induced, and that the shear deformation zone formation was due to the fact we hypothesized was due to the fact to the increase in molecular mobility that is more important than the change in entanglement density. And really, we expected ductile behavior, but we saw an embrittlement, which left us with some open questions. So really, this next area is really trying to answer why are we seeing this embrittlement? What controls the failure response in the ultra-thin glassy systems? So if we can think about this, we're going to really try to decouple the role of entanglements and mobility in these failure stresses. So we went back into the literature to look at how entanglements and mobility have been shown in the bulk to change these failure stresses. So one, in terms of the entanglements, which is more classically thought of a tunable thing to change your mechanical properties, is one, you have this failure stress plotted as a function of the number of entanglements per chain, or MN over ME for Mikos and Pepes. And you can see that below a critical entanglement length or number of entanglements around 10, that you start to have a drop off in your strength, but above which you seem to have a plateau. So this is one way to tune that failure properties. And so our hypothesis makes sense, but we can also look at mobility. And this is often what we forget about, is that if you look at the stress strain curve from Eric Baer's group, which I initially showed you, these first curves here are with an increase in mobility or increase in that temperature. And you can see that that failure stress decreases, but so does the failure strain. So these become more embrittled before they transition into that ductile-like state. So this led to us looking a little bit deeper into the data to look at the changes in failure stresses. And so we have these 4 literature data sets, and you can see that as failure stress as a function of temperature and its relationship to the glass transition temperature, that's actually a very linear decrease, where even around where room temperature is, around here, around 40, but near the glass transition temperature, we decrease around 10 to 20 megapascals. So we now have to think about the fact that when you increase your mobility in your system, you also have a change in your failure stresses. So we know that in decreasing entanglements in your system or increasing mobility, in your mobility leads to a decrease in failure stress. We know both of these change in the same way as we decrease our thickness. So it leads to the question, how are each of these contributing to the changes in failure stresses and that decrease in these systems? So to probe this, in collaboration with Dr. Shinichiro Shimotomura, who was a visiting postdoc in our group back when I was a second year, so a very long time ago, we did a fixed thickness study where we only changed the number of entanglements per chain of 100 nanometer thick polystyrene film. And so the size of the molecules here range from 16 nanometers up to 97 nanometers. So we're not in a confined state. So the only thing that we're changing is those entanglements per chain. So first, we're going to look at that to understand what those properties, how that impacts this failure stresses. And then we're going to use what we learned from that fixed thickness study to inform a study that I did on confined films, where we now pick 3 different molecular weights, where this was the molecular weight I showed you previously in that first area, and now 2 higher molecular weights, where the molecule sizes range from 49 to 62 nanometers, where the entanglements per chain are now 33 and 52. So we're much more in an entangled state. And so the thicknesses that we're going to look at are from 10 nanometers now, so much thinner than the previous project, up to 60 nanometers. And so really looking at, can we understand whether or not it's the entanglement effect or the mobility effect leading to these decreases, and can we pull out those individual contributions from what we learned from these two areas? So for the fixed thickness study, where we look at these 100 nanometer thick polymer films, here we have a stress strain behavior, where you can see again, we see that linear regime, a yield, and a plateau. But if you notice that lowest molecular weight, where we only have 3 entanglements per chain, we have an embrittlement behavior. And we can look a little bit further into the parameter that we look for a failure, which is the maximum stress. And so you can see that maximum stress plotted as a number of entanglements per chain, or MN over ME. We have that drop off where we have around those 3 entanglements per chain. So we can compare to literature data again, and we see relatively good agreement between the literature data and our data. And there's an interesting model that was developed by Mikos and Pepes, which describes one, the maximum stress and the failure stresses and how they change as the number of entanglements per chain. And so we now have a model that describes how entanglements per chain impact failure stress. And so we're going to use this to inform our confined thickness study and understand how entanglements contribute to these ultra thin states. To look at the confined thickness study, we're going to look at these 3 molecular weights. And you can and pick these out where you can see where they are on these curves. So now we have a representative stress strain curves for all 3 of the molecular weights. And I'm going to draw your attention to really just the blue curve down here. So now where I only went down to 20 nanometers in the initial study, now I've decreased to 15 nanometers. So you can see that we have a larger drop off in that stress strain. But if you look at the 2 higher molecular weights now, where this blue curve is 10 nanometers and this blue curve is 15 nanometers, you can clearly see that there's a molecular weight dependence on these stress strain behaviors, especially in terms of that maximum stress. We're going to probe this a little bit more and pull those parameters out. But now, even just looking at these stress strains, we can think about that. But before we pull out the parameter, I'm going to check that we still see that transition from crazing to shear deformation zones. And we do. So here's a nice phase diagram of molecular weight plotted as a function of thickness, where red is crazes and the open squares in blue are shear deformation zones. And so we see it at the 2 higher molecular weights. And we really see a weak dependence on molecular weight for this transition from crazing to shear deformation zones. And this wasn't really that surprising to us, because our initial hypothesis of changing average molecular mobility leading to this has been shown to be molecular weight independent. So again, it supports that hypothesis that mobility really does matter in these systems. So if we now look at the maximum stresses, which we were really interested about as a function of thickness for that lowest molecular weight, you can see that new data point, we have that large drop off. But if we increase our molecular weight to 553 kilodalton, again, we see a slight decrease, but not as large of a magnitude as that lowest molecular weight. And if we increase to our highest molecular weight, again, we see a decrease, but we're not getting down to that 10 megapascal, those really brittle films. So led to us to go back to what we know about failure stresses in these 2 models that I showed you before, but now we're going to create a model based on 1, the entanglements that was developed by Mikos and Pepes, and 2, we're now going to make a semi-empirical model in terms of mobility, where we know that this is a linear decrease from the literature. So we'll use A and B as fitting parameters. So now we know in bulk how failure stress changes as a function of entanglements and mobility, but there's also some work done in the thickness state. 1, how entanglements change as a function of thickness, and 2, how mobility changes as a function of thickness from previous literature. So we can take these 4 as our ingredients, and I'm not going to go into the details of how we do this, but I'm welcome to any questions after of how we get to these models. We can now create this semi-empirical model of the ultra-thin film failure stress as a function of molecular weight and thickness, where we're now taking account of the effects of entanglement and mobility in one equation set. So we can plot our model as a function on top of our experimental data. Now we have failure stress, or sigma F, as a function of thickness. And you can see that we have, where the solid lines here are our model, and you can see our experiment data, and you can see we have relatively good agreement between the 2 data sets, though I argue that this lowest data point doesn't quite agree with our model, and we're still thinking about why that is. But the nice thing about this model, because we added the entanglements and the mobility separately into the system, we can now pull them out and see how their relative contributions occur and which one controls these failure stresses more. So note that this plot looks very complicated. I'll walk you through it. So here we have a relative contribution as a function of thickness for entanglements and mobility. So for the entanglements are the solid colored lines here, and the dashed line is the mobility. So if we first look at the mobility, as we decrease our thickness, one, it's molecular weight independent, and two, it seems it increases its influence on the properties as you decrease your thickness. In terms of the entanglements, this is molecular weight dependent. So this is dependent on the number of entanglements per chain, or the Mn over Me. So if you only have 2.5 entanglements per chain, the entanglements have more of an influence on the properties than the mobility. And this is also shown if we think about that 3 entanglements per chain, which we measured in that 150 nanometer film, where we saw that embrittlement in that lowest molecular weight, where there's 3 entanglements per chain. So this confirms that our model works, at least in the bulk state. So we also can look at, if we increase our molecular weight higher to around 7 to 43 entanglements per chain, that now the mobility matters more than the entanglement changes. And only at the lowest thicknesses, around 10 nanometers, does the entanglement start to play an influence, changes in entanglement start to play an influence on our mechanical properties. So really, you need to, one, take into account what your molecular weights are in your system, but you don't need to go to an infinite molecular weight, because you will always hit a certain plateau. And two, the mobility changes really do need to be taken into account in terms of these mechanical properties, and they're often forgotten about. So now we kind of have some design guidelines for those future applications for those thin film studies to look at how to change the properties, where oftentimes we just think about increasing the molecular weight. So really, that embrittlement, one of the things that you can think about is that right now, embrittlement will always occur at a critical thickness limit. We have to think about how to overcome that. So with this, I was able to, one, understand further what controls these glassy polymer systems. And using Tut-Tut, we looked at 100 nanometer thick polymer films for multiple different molecular weights. And then we did a confined thickness study for 3 different molecular weights. We again observed that transition from crazing the shear formation zones, which confirms our first area that we saw. And that we now have developed this semi-empirical model that captures, one, the role of mobility, and two, the role of entanglements on these failure properties as a function of molecular weight and thickness for the first time. And there's some really interesting work that's coming out that we're doing with Rob Riggleman's group to confirm this model with their simulations. So with that, really wraps up my PhD work. One, I looked at the thickness effects on where we saw the first observation of this transition from crazing the shear deformation zones. And then now we understand what controls these properties, where really the molecular mobility changes have a larger influence on the properties when you have a high molecular weight polymer film. So you, one, have to consider those molecular weights. So if we think now from all of my work, from my PhD and from my previous, even in my everyday life, I think about the limitations of many polymer films. This can be from single use. So we think about the recyclability problem, where many times a lot of the plastics that we put in our single use get thrown away, even if we recycle them, to that thickness limitation that I just talked about, to coming from non-renewable resources like petroleum-based products. And one of my favorite examples of this is the bicycle helmet, as I'm a very avid bike rider, and I know some of you are too in Boulder, as it's one of my main modes of transportation. If you crash, you have to, and hit your head or hit the helmet, you have to you're supposed to throw it away and replace it, because you don't know what micro defects are in those systems. So can you imagine if we could make a helmet that's self-regenerating and has self-healing properties, where we don't have to throw them away into that single-use waste stream? It's really these next generation of polymers is one of the grandstanding challenges, is trying to create these self-sustaining, self-healing polymer systems that have programmable properties. While we've been trying to do it in synthetic systems, there's already a system out there that has existed, and I think is really interesting, is biological systems. So one of the new emerging fields is engineered living materials. And as Ryan hinted at, I've started working on it in my postdoc, and I'm very excited to continue working on it in my future career, where they look at leveraging biological systems to create functional materials, where specifically we can think of bacteria that produce polymeric substances or polymeric matrices that you can control through genetic engineering and control the mechanical properties. So really, and one of the limitations that's been happening where this has been really this emerging field is understanding these structure property relationships, as these systems are pretty complex and dynamic in nature. So really in my independent career, I'm really seeking to characterize and leverage these biological systems to develop these polymeric materials for different applications. And as such, for my postdoc, I saw one with Sujit Datta's lab at Princeton University, because they're experts in living materials in complex systems, specifically at porous media, where one of the postdocs here, Tapamoy Bhattacharjee, has developed this 3D printing system where they're able to print bacteria into structural communities through into porous media systems, where one, they look more at the biophysics and they're looking at non-biofilm forming bacteria, but you can see they have this nice Princeton shield they've printed, and they can look down to a single cell level. So really, I joined this lab to understand these properties, and really now looking at using 3D printing of biofilms, so these bacteria that form these polymeric substances, and printing them into porous media to understand if we can spatially program them into different structures, and really trying to develop fundamental rules to understand the properties that in spatial morphologies we get. And this is some of the preliminary work that I've done here, where we have this very complex looking system, where this is actually a Vibrio cholera film that's grown out and escaped, but really fun to play with. I'm also looking at using bacteria to make self-healing composite systems, where here these bacteria produce nanocellulose at air interfaces. So can you, if you have a hole, will the bacteria migrate to that hole and self-heal? And then one of the last areas I'm very excited about that to get started working on is been inspired by Will Schubert's group on here at CU Boulder, as many probably know, where he uses bacteria to make these bioconcretes, but we're taking it a step back and using those bacteria that produce those calcium carbonate deposits and putting them into different hydrogels and seeing how the mechanics change as a function of the bacteria in the system. So with that, I really want to use those skills that I've leveraged and gained from my PhD and my postdoc in PhD in biofilms and biophysics and bioprinting and polymer mechanics and polymer engineering to really create this huli materials lab, where huli in Hawaiian, as I'm part native Hawaiian, means to change or to study. And it's also the part of the plant here that is the stalk of the taro plant. So this is also called the huli. And so the huli is planted into the ground and the leaves and the root are grown. So this is a taro plant. So it's very well eaten. It's one of the staples in Hawaii, where they'll cut off the root and the leaves and use it for a food source, and they'll replant that stalk or that huli into the ground and create this regenerating life cycle. So really my future independent career is really inspired by this, where we'll have two areas really looking, one at the fundamental sides for the huli side, and then really trying to create functional materials, where some of the first projects will be one looking at the extreme mechanics of biofilms, so really more on the fundamental, but using bioprinting to create stimuli responsive polymer actuators with biofilms, to programming at the molecular level, the mechanical properties, and looking at interesting cell connectivity behaviors to create interesting polymer hydrogel behaviors. And so with that, I'd like to thank you for your attention. NSF for the funding for my PhD work, and my group, the Crosby Group, and Al Crosby, as Ryan mentioned, was my PhD advisor. And then I'm funded here at Princeton for the Presidential Postdoctoral Fellowship. And as it just started in July, this is really how I've seen the entire group. So we've done social distance gatherings, and I welcome any questions.
Fantastic. Thank you so much, Kanani. So I apologize. I failed to mention at the beginning that everyone is muted, and so should raise their hand or type questions in the chat. So please, if you have questions, James and I will monitor and try to unmute you if you'd like to ask a question. I can ask a couple to start, maybe. So Kanani, I thought this was a really interesting trade-off that you mentioned between the role of decreasing entanglements, but then also increasing mobility. Polystyrene, as far as I understand it, is maybe unusual, or at least has a very strong response as far as its suppression in TG and increase in mobility. And so I was just wondering what you thought about prospects for other polymer chemistries, and whether that would be interesting to look at other systems that might have weaker or sometimes almost no effect, if I understand correctly.
Yeah, I think polyalpha methylstyrene has been shown to have no mobile surface layer, so I think that would be interesting. Though Chris Stafford's group has shown that it has a decrease in elastic modulus with their measurement system for surface wrinkling. So I think that would be interesting. I think also trying cross-linking systems in the alternate states and seeing if those change, because it's such a new system in terms of the mechanical measurement technique. Most of the focus has now been on the electronic side and less on the polymer physics. I think there's so much to explore.
Mm-hmm.
I know Al is doing block copolymer work now.
Mm-hmm. Cool. Okay. I saw Tim's hand go up, so I'll allow him to unmute.
All right. Thanks, Ryan, for unmuting me. Yeah, great talk, Kanani. I just naturally thought of a paper that I'm not too familiar with from Rich Vaya and Ned Thomas. I don't know if you've seen this, but they've done some work in like polystyrene thin films where they've seen some extreme energy absorption.
Mm-hmm.
I mean, does your work sort of fill in the blanks as to why they see that? And then also, what do you feel like, are there unexplored opportunities here in that space as it relates to sort of extremely thin polymer films?
Yeah, I think their work is really interesting. I've seen Ned give that talk so many times that I think it's burned into my brain. I think theirs one is trying to do like a mobility measurement where you actually measure them at different temperatures, because what they're seeing is a like adiabatic heating. So if we can do a high strain rate, some of the work I've done on the freestanding kind of relates to that, where this is unpublished and probably will never be published, where we were putting a high-speed camera and looking at how fast the fracture was happening, and I had to get up to 1,000 frames per second to capture those failures. So I think those are some very interesting opportunities. And then also trying to stick these into a DMA and seeing if you could measure the ME, the entanglement microwave, because that's typically how you measure them, and seeing if we could get up to those parameters and not just me pulling out, oh, this is what is typical.
Yeah, no, I agree. There's some interesting stuff in there, but yeah, I've seen Ned and Rich talk about it quite a bit too, and never fully understood the mechanisms and the nuances. And then, seeing your work here, it seemed obvious there was some potentially interplay. So thanks.
Yeah.
Okay, Saul Husseini.
Hi,
Hello.
I'm Sal. I'm a transfer student, incoming transfer student, basically, first semester here. I would like to suggest there is a good material called which is derived from brown algae, with sodium alginate, which will be a great, I think, self-healing material you can add to your polymers and see, because it is a polymer itself.
Yeah, I think there's some interesting opportunities to explore in terms of going thin, in terms of the alginates, or introducing composite structures. So we've also done work where we've introduced nanocomposites, where oftentimes when you introduce a nanoparticle, it increases the strength. But unfortunately, we're doing polymethyl methacrylate on water, and polymethyl methacrylate does not like water. So we weren't seeing some interesting behavior. But
Okay.
I think that there's opportunities to strengthen them. This technique is it originally was created in 2015. So that's why we started with the model system. But I think there's many different opportunities to go into different polymers.
Okay, great. So we have a couple of questions in the chat. I'll read the one from Dana first. What differences did you observe in measurements collected using the liquid-based tut-tut system versus the liquid-free TUF system?
I have this nice slide for you. So one of the things is that with the freestanding system, we can only go down to 30 nanometers in thickness because they're so difficult to handle. I wish I got further down thinner, but so we're not going into the ultra confined state, though I was able to measure 1 million molecular weight, so really high. So these were technically confined. But we didn't see an effect in terms of the elastic modulus or the maximum stress. The thing that we saw that was a very interesting behavior was no matter what I did, I wasn't able to get these very long ductile like behaviors in these freestanding. They always broke fast or they always snapped. So what we think was happening is that with the fact that the crazes are fibrillate structures and that the capillary length of water is around 2.7 millimeters, that we're having water infiltrating into the system and acting as a stabilizer. And so we're not getting that same embrittlement effect. Does that answer your question, Dana?
Dana is muted. Let's see if I can find her.
She's on video right now.
Okay. Yes, thumbs up. All right, excellent. So Alina says, what is the softest material you can or have measured in this system?
So do you mean softest by the elastic modulus or?
I will try to find Alina. Where is Alina?
That's an interesting question in terms of what's soft.
Yes, modulus, she says.
Modulus. Okay. So the softest I've gone is for the work that I've done is around like 2 gigapascals. We've also worked down to there was some PDMS that's been done. So we've I think it was 0.5 megapascals. It was pretty stiff PDMS. The issue of going softer in these systems sometimes, and like you have to think about, is that the water starts to play a larger role in terms of surface tension. So you have to account for the surface tension effects a little bit more in your measurement system. But I think going soft, like it's not a limitation, it's just you have to think about it more.
Okay, great. I thought I saw another hand go up, but now I don't see it. Was there someone else? Oh, new chat.
Ryan, I could ask another question.
Okay, go ahead, Tim.
I unmuted myself somehow. Related to that, when I naturally think about like really thin polymer films, I start thinking, and I'm not a polymer physicist by any means, but I start thinking about, a deviation from kind of the expected behavior, and you're seeing that here. I mean, are there sort of computational aspects of this that could be extended, or have you overturned anything that would be something that you could imagine partnering with in that space as well?
Yeah, so we've Al actually has a grant right now with Rob Riggleman's group for the thin film. Hopefully that's what you're asking, right? In terms of the thin film systems. Yeah, and so this entanglement project, we're actually writing up the paper with Rob Riggleman. So I didn't show any of the simulations, but they see very similar behavior, except for they don't get any defects. So they actually have increase in toughness. Their curves look very different than ours, but they've been able to show for a different paper that they can get agreement between the simulation and the experiments and get a collapse of the data. They created this model that accounts for the changes in entanglement. So now we're trying to apply the changes in mobility because they're able to pull those two numbers directly out where we're just making assumptions. So yeah, I think the simulation is key to understanding a lot of these changes.
Kanani, as Tim was asking that question, I had another thought or question, which is, so in the thin film nano confinement TG world, people use a lot of fluorescence measurements, fluorescence lifetime and things like that to look at mobility. Have you thought about trying to combine some of that fluorescence imaging with these deformation mechanisms?
Yeah, there's the grad student who's, you know Cindy, but the grad student who took over this project for me is putting mechanophores into the polystyrene to see where they break.
Cool. Okay, other questions?
Ryan, could I ask a quick question?
Yes, please, Charles.
Have you tried anything like where you could take the periodicity of the polymer and see how it could couple with the periodicity and the deformation? For example, using something like a block copolymer?
Mhm. Yeah, I think that's a very interesting question because you can put I haven't done it, but Al and Rob has thought about that where they put in a rubbery block that doesn't form these shootout formation zones and then one that forms these crazes and looking at those behaviors. And I don't know where they are in those experiments, but I know they've been thinking about those periodicity and doing lamellar spacing within film behavior.
And one other quick question. I wonder if there, this is not my field, so these questions are kind of naive, but using kind of the patterns that you can form as a template for self-assembly or for maybe some kind of mechanical lithography.
Mm-hmm. Yeah, there's been some interesting thoughts about trying to use crazes. I know because you actually can get more tougher behavior if you have a craze, about back infilling with a craze in putting in a different polymer system. I know there's been thoughts about potentially using them in filtration membranes, or there's been interesting work where you have sandwich structures where if you have a soft and a film that crazes and you stretch them, you get more ductility in them. So there's many opportunities to play around. The crazes, well, they've been studied from the 70s, they kind of dropped off and then kind of gained popularity back in the last 5 years or so, at least when I started working back on them.
Interesting. Thanks. Neat.
Yeah.
Okay, James informs me that you all should have the power to unmute yourself now. So if there's other questions, you can. Oh, Alexa wants to ask a question. Alexa, since you can unmute yourself, I'll let you do it directly.
No way, really?
Yes, way.
Hey, Kanani, that was a great talk.
Thanks, Alexa.
I was curious. I guess you've heard I'm now an amateur rheologist. So I was curious if you could speak to if there was any possibility to extend this technique to look at things like frequency dependent responses. So for example, if you get this thing going and maybe a hertz or slower, maybe you could measure tan delta or something. And
yeah.
Yes, okay, great. And then do you expect there to be any interesting, I don't know, phenomena that would arise as you start to get into this nano confinement regime?
I'm not sure. I think you would, in terms of as you get that more mobile layer and that more larger influence of the mobility, I think you would have a difference in the behavior in terms of that tan delta. But yeah, that's a good question. That was actually in the original proposal that we did not get into. There's too many things to explore.
Yeah, for sure. Cool. Well, you might have been in grad school for another 5 years if you had to do that. Okay, I'm going to mute myself again now, Ryan. Thanks, Kanane. Great talk.
Thanks.
Okay.
One quick question.
Yeah.
Which materials were you using? Like, were they produced by CVD by any chance?
No, these were all spin coated. So we took polystyrene that we bought from Polymer Source, and then we put them into a solvent, and then we spin coat them around 3,000 RPM. It depends. The concentration depends on what thickness you want or molecular weight you have, and then we get our film, and then we put them to anneal. I know there's been talks about trying to put CVD systems in there. We've also put ultra stable glasses, but they're very brittle, so we didn't have much success on that.
Yeah, nice talk there. I enjoyed it.
Thank you.
Okay, any other questions? If not, let's thank Kanane again for a great talk and for visiting.
Thank you, everyone.
Being blinded by the sun now. It's very sunny here in Colorado. You should know that.
Yeah, thanks, Kanane. Very good talk.
Thanks.
We'll see you.
See ya.
Thank you.
See you tomorrow.
Great. Enjoyed your talk. Thank you.
Hey,
Bye.
Ryan, am I supposed to use the other link now or what?
Good job, Kanane.
I
Thanks, Kayla.
think so, but I don't see any reason